Welcome to the June's Science and Math Interest Group of SMIG meeting. Today's speaker needs no introduction. Mark Edelman has been member of Summit Ograd for quite some time. He was actually a director of Summit Ograd, I think it was 2 years ago. Mark attended the University of Chicago and the University of Buffalo. His career included government work, computer consulting, and compliance work on information systems in the pharmaceutical industry. He has a lifelong interest in science and its history, and especially in the natural sciences. This is how he learned about today's topic, the Earth magnetic field. So Mark, the microphone and the camera is yours.
Thank you very much. First thing I'm going to do is share my screen. The topic today is the Earth's magnetic field. I think it's a great thing to talk about. It has a good history, fascinating scientific theory, vital importance, and serious risks. I want to make a disclaimer. I'm not, I hear sirens. Can't help it. I'm not an expert. I'm an enthusiast. I've taken an interest in this and I've learned something about it, and I'd like to share what I've learned. If you have a broad question or comment, I'd like you to save it until the end. If you have a specific question while I'm bringing something up, please interrupt me and we'll get a quick answer. And I'd like to just mention, because people forget, that the easiest, quickest way to unmute yourself is to hold the space bar down on your keyboard. So you can try that anytime and you'll see the mute symbol change and you'll see that it's working. Okay, I'm going to jump around quite a bit and in terms of topics, and you may wonder why. And the reason is that there are so many different areas of knowledge that have to come together to end up with what we know today about the Earth's magnetic field. I'd like to begin with a little trivia question. With regard to magnetism, why should Canada come to mind? Hold your answers until the end of the hour. So let's begin with some background. Magnetism is not noticeable without a little technology. In the Stone Age and in the Bronze Age, probably few people were aware of it. But with the Iron Age, it was seen that lodestone, called magnetite, has iron in it and is attracted to iron. Here's a magnet sticking to a lodestone. The Greeks named magnetism after Magnus, which was the name of a son of Zeus, who was a hero in Homer. And there was a place in Greece called Magnesia. If you put a piece of lodestone on a little raft floating in water, as you see in the picture, it will orient itself, making a compass. Such compasses were known and used in Europe by the 13th century. Let's describe the compass the way we know it today. It's a needle of iron that has been magnetized, possibly by stroking it with magnetite. If it's balanced on a bearing, one end will turn to point in a fixed direction, and when it does that, we call it magnetic north. But we also know true north or geographic north. Now that's from astronomy and geometry. This knowledge is very old. The Greeks understood spherical Earth and latitude and longitude. The angle between true north and magnetic or compass north is called declination. And in North America, the compass tends to point a few degrees to the left of true north, and that's a negative declination. Also, from ancient Babylonia, we get 360 degrees in a circle. So it's traditional for us to put degrees on an astronomical instrument, on a globe, and on a compass to indicate direction or angle. Your phone has a magnetic compass built into it. This is mine. Let's look at the left side of the picture. You see the little red arrow, and it's pointing to magnetic north. This phone happened to be oriented a little differently from magnetic north, so that's the white, I can't make the arrow more here. That's the white line there. That's the way the phone is oriented. So the bearing of the phone relative to magnetic north is 343 degrees. Now I turned on a feature on the right-hand side, and it's called declination correction. You see the little arrow is pointing a slightly different way. Now it's pointing toward true north. And you see that the bearing of the phone is different. Now it reads 330 degrees based on true north. So how did the phone know the direction of true north? Well, it accessed the GPS, which supplied the location, the latitude and longitude, and then it looked up the declination at that location, and then it made a correction. Okay. If this is confusing, let's try another little approach with a diagram. Here you see true north, and you see magnetic north. This is a positive declination in this case. And you see the angle D, which is the amount of declination. But there's something else going on. The compass, if you put it on an edge like this, will point downwards in the northern hemisphere. And that is called inclination. So if you travel north toward the North Pole, the inclination will increase. And at the magnetic North Pole, it should be 90 degrees, pointing straight down. If you go back toward the equator, it should go to 0 degrees. One thing the compass does not measure is the intensity of the magnetic field. It varies, but the average intensity of the Earth's field is about 0.6 Oersted. That is much weaker, 1,000 times weaker than a refrigerator magnet. When we use a compass, we're assuming a model of the terrestrial magnetism. It's called the dipole model. We imagine that the Earth has a straight bar magnet stuck through the center of the Earth. And based on that, we define the geomagnetic poles. But the truth is that this model is a lot simpler than the Earth. So the geomagnetic poles are not exactly the same as the actual magnetic poles, which would be found using a compass. Now, we've all seen pictures of a magnet making iron filings form into those curves, which start at one pole and then they swing out and they end up at the other pole. You follow one of those lines with a compass and you will always end up at the magnetic pole. And by the way, what kind of magnetic pole is up there in the Arctic? Well, by convention, a compass needle points north. And that means it's attracted to its opposite. So what is that? That's a south magnetic pole. Now, the poles were first described scientifically all the way back in 1269 by Petrus Peregrinus, which means Peter the Pilgrim. He experimented with lodestones. He observed that if you divide a lodestone, it creates two smaller ones, and each one has its own poles. It was also known that magnetism could be spread to a piece of iron by stroking it with magnetite. These two facts implied that magnetism is a natural property of a material. It's not magic. Petrus was a logical thinker. In 1600, William Gilbert, an Englishman, published the first major scientific work called De Magneti. And if you read it, it reads like modern experimental science. One of the things he did was he carved lodestones into spheres like the Earth, and he charted their interactions. This was modeling. His models led him to the insight that magnetism is not just in lodestones and compasses, but it must be a property of the Earth itself. So the Earth acts like a magnet and the compass is attracted. Therefore, the Earth must have poles. That's why the compass is pointing to one of them. By the 17th century, navigation across the open ocean was widespread, and so the compass was a vital instrument. But the trouble is that the magnetic declination was extremely irregular across the oceans, and it was unstable. In 1634, someone named Henry Gellibrand, a mathematician, reviewed the records of declination near London. He found out that it had changed by 7 degrees just in 54 years. It was startling that the Earth, which was commonly assumed to be fundamentally unchanging, was actually dynamic. For navigation, up-to-date declinations are needed. Increasingly, they were collected, mapped, and shared. This was one of the first global databases. Now, here is a map of declinations. And if you look at it, you will see that here's North America. And you can see that in our area, the declination is in the vicinity of -10 degrees. And that matches up to what I found on my phone when I used the compass. That was 13 degrees. And the trouble is, of course, that the declinations are not stable. But people went out and they started measuring them across the oceans. One of those people was Edmund Halley, the astronomer. He spent a couple of years measuring declination across the Atlantic Ocean. So in 1700, he published his map. And this is the kind of map he published. It's called an isogonic map, where you draw the lines of equal declination. So along this line, the declination is a 0, and the compass will point to the true north. And now what we see is what's happened to declinations over the years. This animation represents data collected since 1590 and translated into a modern map. And you see that declination has been unstable all the time. It just keeps going, keeps shifting all the time. This is old science. Now, you might imagine that today, with our GPS, we don't need declinations or even compasses for navigation. Well, that's not so. Here's an example. This number, what does it mean? Airport runways have numbers. The number is the magnetic compass bearing divided by 10. So every airport runway has numbers at each end. Each number is the airplane's compass bearing when it's landing on from that end of the airport. Aviation still uses the magnetic compass. Why? Because it's still the most reliable way to measure direction. In this slide, you see an airplane landing, and its bearing is 220 degrees southwest, and the runway is numbered 22. And that's how it works. However, since declinations change, sometimes runways actually have to be renumbered at great expense. A recent example was in Geneva, Switzerland. They had to change the numbers on one of their runways. So declination is still being mapped and remapped today. Now, for ocean navigation, the compass bearing is useful, but it's not sufficient. You need reliable measures of latitude and longitude in order to place yourself on a map or to make a map. You can measure latitude by the angle of the sun at its zenith during the day. And then you would make an adjustment for the date in the year. Latitude depends on the well-known geometry of the solar system, which causes the sun to rise and set on the Earth, and its maximum height varies with latitude and also varies in an annual cycle. Longitude is different because it's arbitrary. Now, by convention, the 0 of longitude goes through Greenwich, England. As you move east or west, the longitude changes, and there are 360 degrees around the planet. Since the Earth revolves once per day, 360 degrees corresponds to about 24 hours. So that gives you a way to determine longitude. If you were sailing somewhere, let's say that you had a clock, and in the middle of the day, you observe the sun, and you observe when it's at its highest angle, and then you set the clock to noon. So that's your local time. Now you need a second clock, and that clock was set to the time in Greenwich, England. From the difference between the two clocks, you can derive your longitude. Trouble is, of course, that the clock that was set to Greenwich time has been on your ship for a long time already, and clocks have a hard time when they're in the heaving ocean. The challenge of accurate clocks or chronometers on ships was so serious that the British government offered a huge prize for the solution. And I wish I had time to talk about that. Meanwhile, declination was and still is vital to navigation. If you have a map of declinations, and if you know your latitude, and you've kept a log, you can generally estimate your location pretty well, including the longitude. Now we're going to digress temporarily from magnetism to electricity, and we're going to mention some history. Now, electricity is different from magnetism. It's easily discovered just by rubbing different materials together to make a spark. And it was actually William Gilbert, the same one who wrote the classic book on magnetism, who actually coined the word electric. In 1746, the Leyden jar was invented by someone named Peter van Musschenbroek, a Dutch physicist. The Leyden jar can store an electric charge. This unleashed a flood of experimentation. You see Leyden jars on the picture on the left. Ben Franklin was a pioneering researcher in the 1700s. First, he proved that lightning was electricity. And then right away, he invented the lightning rod, which I think was the first practical electrical device. He proved that electricity was something that flows through matter. And in 1747, he wrote that materials normally have equal positive and negative charges. But if for some reason they're made unequal, the electricity will try to flow until the equilibrium is restored. Thus, opposite charges attract, which explains the Leyden jar's ability to store them. Then in 1800, Volta invented the pile or battery seen in the center picture. This was the start of experimenting with continuous electrical flow or current. It's nice to see what these scientists looked like. Here's Gilbert, who wrote De Magnete. Here's Halley and Franklin and Volta. And I will mention the others in a minute. To me, meanwhile, you can take a look at these pictures and notice the changes in men's fashion over several centuries. To me, it's so interesting how electricity was always hiding in plain sight. Discoveries like those of Franklin and Volta could have been made much earlier. For example, the battery is just zinc, copper, and salt water. But nobody had the conceptual framework that would suggest the right technology or the right experiments. And certainly the lightning rod could have been invented anytime. Anyway, in 1820, we had Hans Ørsted. He was a Dane, and he was a follower of the philosopher Immanuel Kant. Now, Kant thought that there should be a unifying principle for natural forces, a sort of a theory of everything. And Ørsted really wanted this to be true. So he set up an electric current and he put a compass next to it. And sure enough, the compass was deflected. This was revolutionary. It proved that electricity creates magnetism. And of course, that suggested that magnets must be somehow animated by electric currents. And it was striking that the magnetic direction was perpendicular to the direction of electric current. That was different, it was unexpected. It didn't fit the Newtonian model from gravity, in which a force would point toward its source. After Ørsted, it was easy for anybody to make a strong magnetic field. You just make loops of wire, and the magnetic field is concentrated, as you see in this picture. So suddenly, anybody could make a relatively powerful magnet. We had electric current, and we had coils of wire. So electricity and magnetism could now be created to order in a laboratory. Right away, the next year, Michael Faraday did what Ørsted could have done. He showed that a moving magnet causes current to flow in a wire. In other words, it creates an electric force. This completed the basic conceptual framework. Moving or changing electricity made magnetic force, and moving or changing magnetism made electric force. They were bound together by one principle, just exactly the way Ørsted had hoped, and we call it electromagnetism. It was Faraday who envisioned fields in the modern way as activated regions in space. Now it became possible to think of gravity as a field, which attracted along straight lines. In contrast, magnetism was polar, so its field had a different shape. Faraday thought of fields in terms that we call it lines of force. This concept is valid, and engineers use it, but we don't take it literally. There are no actual lines. The lines are just a mapping of the magnetic force vector. The direction follows those interesting curves, and the intensity could be graphically represented as the density of lines of force. And you see that in this diagram here. The close together lines would represent more intensity. Now let's return to the Earth's magnetism. An explorer named Ross traveled to the actual North Magnetic Pole in 1831. There, the compass pointed down into the Earth with an inclination of 90 degrees. The Magnetic Crusade, as it was called, continued throughout the 19th century and even beyond it. Alexander von Humboldt, the world-famous naturalist, organized observatories around the planet. Carl Friedrich Gauss, the mathematician, invented a reliable magnetometer to measure the magnetic field. The British Navy was constantly measuring it and was a big contributor of data. And all this data was collected, mapped, recorded in books, and so forth. It was understood that for navigation purposes, this task would never finish. And in fact, we still have magnetic surveys today using satellites. And that is why your GPS has a built-in map of declination. So after it determines where you are, it can correct your compass to point toward true north. These maps show recent data, and they remind you that the dipole model of magnetism is simplistic for the Earth. What we have on Earth is very complex. you see how both declination and intensity are highly irregular. You see that strange spot of low intensity over South America. Nobody really knows why that's happening. Meanwhile, in the 19th century, in the 1860s, James Maxwell developed his famous equations of electromagnetism. He brought it all together, the fields and how changes in them would move across space as waves. And he's the one who realized that light is an electromagnetic wave, and he pointed the way toward radio. So now let's jump back to the nature of magnetism itself. Now we know today, we know so much more about it. We know that indeed it starts with electric current, but the electric current is inside of atoms. Electrically charged particles are moving. Mostly that's electrons on the Earth. Most of them are orbiting in atoms, and they're in pairs mostly, with opposite spins, and the magnetic field cancels out. But in some elements, like iron, as shown here, there are unpaired electrons. And as they move, they create a magnetic field. And as adjacent atoms have magnetic fields, there's a tendency for them to align up with each other, making a little bit of net magnetism on a macro scale. And once they line up, they may stay that way. There's a name for that, remanence. The magnetism gets locked in. But if you heat up the material, the atoms get agitated and the magnetic field gets disorganized again. Magnetite, or lodestone, is a form of iron oxide which has remanence. When this material solidified, the magnetic field of the Earth encouraged the molecules to line up, and they got locked in place. So it's possible to say that magnetism is contagious. If there were no disturbances on the Earth, a lot of minerals containing iron could be slowly magnetized in the same direction as the Earth's field. However, over geologic time, there are lots of disturbances. And that's the next topic. Now, geology has progressed a lot. It has progressed a great deal in the 19th century. There was a growing understanding that the Earth itself was changing and that its history could be read in rock formations. And geology also began to focus on the interior of the planet. You may remember that Jules Verne published his famous popular book, Journey to the Center of the Earth, in 1864. That was science fiction. There was plenty of fantasy about the underworld, but one fact was that somehow the Earth's magnetism was being produced inside the planet. By the 1930s, seismic research using earthquakes or explosions had produced the modern model of the Earth's structure. Below the crust, we have the mantle, which is molten rock. Sometimes it breaks through the crust in a volcano. When the lava solidifies, it records the magnetic direction, the magnetic field of its time and place. Below the mantle is the core, which is mostly made, it's molten of course, and it's mostly made of iron and nickel. And then the innermost core of Earth is actually solid because the pressure is so high. The Earth must be generating magnetism from electric currents by the dynamo effect discovered by Faraday, a system in which electric and magnetic fields and motions are interacting. The instability of declination and of intensity begins to make sense, since, of course, the electric currents in the core of the Earth must vary with the movement of materials. They move because of thermal convection, and that movement is modulated by the planet's rotation. Now, in 1905, a French geologist named Bernard Brun studied some rock that had been heated by a volcano and then cooled 5 million years ago. And of course, it recorded the Earth's magnetic field at that time. Brun documented the orientation of his rock samples, and there was an unpleasant surprise. The magnetism pointed in the wrong direction, south instead of north. And he was forced to conclude that the magnetic poles of the Earth had at one time been reversed. His claim was not accepted. Now, back to the dynamo effect. To this day, the Earth's dynamo is not easily explained. First of all, where does the energy come from to make the dynamo run and to generate the magnetic field? Well, largely, it comes from the formation of our planet 4.5 billion years ago, when orbiting matter came together and was compressed by gravity. The potential energy was converted to kinetic energy, or heat. Our planet has been cooling ever since, but it's still hot. Today, the highest internal temperature is around 6,000 degrees Celsius, and that is just as hot as the surface of the sun. If you could see the core, it would be white hot, just like the sun. The second source of energy is radioactivity, which is very abundant below the crust. And a third source of energy is the Earth's rotation. It spins from west to east with an angular momentum that dates all the way back to the origins of the Earth. This spin, of course, is 1 revolution per day, but the day is gradually getting longer due to internal friction making heat. Now, a little side note. If you read about the Earth's core today, you may see a funny statement that says that the core and the inner core rotate in opposite directions. When I read that, I was shocked, so I did some research. It's not quite what it seems. The fact is that if you use your position riding on the Earth's crust as your frame of reference, then the outer core is very slowly falling behind you about 2 degrees every decade. But the inner core is going a little faster than you are going, amounting to 9 degrees per decade. So if you insist, you could say that the inner and the outer cores move in opposite directions relative to the Earth's surface. This is another source of friction, which generates extra heat. So with all this heat and movement, there must be convection. The hotter material closer to the center is rising, and the cooler material that gets denser is sinking. And then this combines with the Earth's rotation, and you get the Coriolis effect, which creates helical motions in the core. And here you see them inaccurately represented, but it gives you the idea of the helical motions. I think a meteorologist would be able to make a better illustration of the Coriolis, the effect of the Coriolis force. So the inner and the outer cores contain material in motion, and much of it is metal with unpaired electrons. Now, if the core were a perfect conductor, there might be much less electrical current. But iron has some resistance. It carries the free electrons around by convection and rotation. This current produces a magnetic field, which in turn induces electric currents elsewhere, and so on and so on. A very complex, unstable system. Thus, the mechanical energy from heat and motion is ultimately responsible for the Earth's magnetic field. And no wonder it's changing. Data from the Earth's dynamo is incomplete. However, we have the sun and we have the other planets to study. For example, the core of Mars, it has already solidified. So there's very little magnetism. Why is this? I guess it's because Mars is a much smaller planet. The sun, on the other hand, is a powerful dynamo with a very strong magnetic field and extreme turbulence. In the sun, the turbulence of heat convection and the dynamo effect combine in such a way as to destabilize and reverse the magnetic field about every 11 years. So there's nothing forbidding the Earth from also reversing its poles. Satellite surveys and modeling show that the Earth's field is very complicated. It's not a dipole. It's more like a pot of spaghetti. It's not a neat spinning top. It's boiling and changing. There are magnetic lines leading in many directions. By the 1950s, after centuries of research, we had the model of the Earth's core and its dynamo effect, producing the magnetic field and its chaotic changes. Meanwhile, another long-standing problem was on its way to a solution. Now, there used to be, actually within our lifetimes, there was a basic conflict between geology and evolutionary biology. Fossils show that our biome is global, including not only the creatures in the seas, but also the big land animals. They are global. So the dinosaurs, for instance, lived on the different continents. So how could the same dinosaur be on different continents? How did they cross the ocean? There were some implausible but persistent hypotheses. The main one was the imagined land bridges connecting the continents. Now, when I was in primary school, there was a map that showed these land bridges. They were portrayed with animals marching across them, single file, from one continent to the other on a sort of a sandbar, and the ocean was on both sides. This is a good example of how when science is stumped, it just kind of stops for a while. sticking with hypotheses that everybody knows to be faulty and waiting for a better idea to appear. Well, it was in 1912 that the geophysicist Alfred Wegener suggested that the continents have moved. He imagined them starting out as a single continent, which he called Pangaea, and they split up about 200 million years ago. This would explain why there's a common biological heritage, yet clearly divergent recent evolution on each continent. It's an utterly logical proposal in terms of evolution, but it didn't seem plausible in geology, so Wegener's idea was not accepted. And then new information emerged. This is such a wonderful story. First, there were more discoveries about magnetism in rocks around the world. Sometimes the magnetic direction was reversed, just as Bernard Brun had found, but often it just pointed in some random direction, as though it had been rotated. For example, a rock formation in India might have a magnetic direction that was west instead of north. Meanwhile, for military reasons after World War II, there was a new type of ocean survey. Sensors were lowered to the seafloor, and the results were remarkable. For example, in the middle of the Atlantic Ocean, there turned out to be a deep gash in the Earth's crust. You see it here. Oops, that was not supposed to happen. Okay. Anyway, in this gash, lava was always coming up, and it was pushing the crust apart. Now, on this map, if you look at the red color, that represents the youngest rock. Okay, and you see where the youngest rock is. It's in these chasms in the ocean. So here was the evidence that would have delighted Wegener. The Atlantic Ocean was widening and the continents were moving apart. And pretty soon, mapping disclosed a global chain of fissures in the crust. What started out as a survey of the oceans became a proof of continental drift. The Americas had moved away from Europe and Africa. It turned out that India had broken off from Africa and rotated, or I should say from Pangaea, and rotated as it collided with Asia. And that's what changed the magnetic direction of its rocks. Suddenly there was a consistency between geology and evolutionary biology. Plate tectonics, as we now call it, explains the variety of orientations of fossil magnetism and the similarity of rock formations on opposite sides of an ocean, as well as the commonalities of animals on different continents. And it also explains the major mountain ranges, such as the Andes or the Himalayas, where the Earth's crust has been crumpled by compression. And then the discoveries got even better. Magnetic surveys found stripes along the bottom of the sea with opposite magnetic orientation. In other words, as the ocean widened and new rock was formed on the ocean floor, it froze the magnetic direction of its time, and this direction kept reversing. So it turns out that the Earth's poles have reversed hundreds of times. On average, a reversal occurs every few million years. Lately, the frequency has increased, but the overall pattern looks random. The last occurrence of a pole reversal was about 780,000 years ago. It took some time, about 10,000 years. During that period, the magnetic field of the Earth was weak and disorganized. So, what happened to life when the poles reversed? Well, there was not a mass extinction, but we do know that some animals, such as birds and fish, use a magnetic sense for migrations. When the poles reversed, some species failed to adapt and they died out. Recently, there's been sensationalized reporting about an imminent pole reversal. They say it's overdue. But the chaotic pattern from the past doesn't really back that up. Another argument for reversal is that the magnetic field is getting weaker, about 6% each century. But that's not unusual either. A third point is that in the South American region, as you saw earlier, there's an anomaly, a vast area with an extremely weak field, as we saw. No one knows why, but it is relatively recent. So perhaps that's a sign of a pole reversal to come. Finally, the most dramatic reason that some people think we may have a pole reversal is that the magnetic poles are moving. Now, you remember that in 1831, Ross reached the North Pole in Canada. Since then, it has migrated very far, and today it is moving across the Arctic Ocean. But the pole has migrated before. According to recent measurements of volcanic rock in Iceland, just 2,000 or 3,000 years ago, the North Magnetic Pole was located nearby in Norway. And you know, this suggests that the ancient Greeks would have been able to see the aurora borealis at night. And that would explain why Aristotle made reference to it in his books. In fact, right now, the magnetic North Pole is passing close to the geographic pole. It has moved at an incredible rate of 55 kilometers per year. Meanwhile, the South Pole is also moving, but much less. Something is afoot. Today, satellites are mapping geomagnetism in fine detail every day. Changes in the magnetic field affect the ionosphere, radio communication, the GPS system, aviation, electric power grids, and much more. Imagine if we were informed this year that the Earth's field were collapsing, predicting some magnetic chaos followed by a possible pole reversal. What difference would it make to us? Well, it would be a serious threat because the Earth's magnetic field is also a shield protecting us from what's called space weather, which originates in the sun. Let's consider the sun. It's not a smooth round ball giving off a steady heat, no. We know today that the sun is a turbulent dynamo, like the inner Earth, but far, far bigger and faster. The sun is mostly made of charged particles, and they're moving. The electromagnetic forces are so strong that they constantly eject particles, which we call the solar wind. These atomic nuclei and electrons are speeding out from the sun in all directions all the time. The solar wind could blow away our atmosphere. It has already blown away much or most of the Martian atmosphere. We are protected from the solar particles by the magnetosphere. Well, it's not a sphere, but it's the shape of the magnetic field of the Earth. This shape is distorted by the incoming solar wind. Remember, a charged particle in motion is an electric current, which has its own magnetic field, which interacts with the Earth's magnetic field. The net effect of this is similar to two magnets repelling each other. The particles are deflected, and they tend to follow the magnetic lines instead of hitting the Earth. And you see that illustrated here. It's under that umbrella that we live, protected from space weather. Now, were the magnetosphere to deteriorate, we would experience dangerous radiation and huge electric currents on the Earth. In fact, the sun frequently has what are called coronal mass ejections, CMEs. That means a huge amount of matter suddenly explodes out from the sun toward the planets. It takes from 13 hours up to several days to reach the Earth's orbit. A very small fraction of CMEs actually strike the Earth. In 1859, there was one CME called the Carrington event. Carrington observed the eruption through a telescope. This is the kind of thing he saw. And this is the size of the Earth. When he observed it, the light had taken 8.5 minutes to go from the sun to the Earth. A day later, the charged particles came. Telegraph lines everywhere were sparking or they burnt out, and other devices were damaged. This is 1859. In those days, there wasn't much electrical equipment. A solar storm can be really, really big. On July 23rd, 2012, there was a CME that was the strongest observed since the Carrington event. It was observed from a satellite. Luckily, it was not pointing toward the Earth. An analysis was done at that time, which concluded that if it had hit the Earth, there would have been a global infrastructure disaster. Damage to the US alone was estimated in the trillions of dollars, trillions. And recovery time for the infrastructure was thought to be up to 10 years. Well, I almost forgot about the question I asked at the start of this hour. Does anybody recall the question? It was, with regard to magnetism, why should Canada come to mind? Does anybody want to volunteer an answer? I don't really expect one, but I have two answers. One is false and one is true. Let's have the false answer. The false answer would be Canada is the home of the North Pole, the magnetic pole. Well, that's not true, but it used to be. The pole left Canada years ago, and as we saw, it's headed towards Siberia. But here's something that is true. If you go to Canada, the Canadian coins are slightly magnetic. So if you go there, don't put your credit card next to those coins in your pocket. thank you all very much for listening. And now I will take questions.
Okay, Mark, thank you very much for a wonderful talk.
Yeah,
Anyone has a Alejo?
good,
That's now it's working. Yes.
good.
So thank you for a most enjoyable and informative talk. I often wondered, what is magnetism? And I'm not sure I still know the full answer to that question, but it's intriguing. The question I really have is, you mentioned physicists want to have a theory of everything. Why are they having such a hard time understanding quantum gravity?
Well, I don't know, but that's way, way beyond the scope of my presentation. I don't know why they're having such a hard time, but I know that if I were them, I'd probably have a hard time too. I can't give you a better answer than that today or maybe any day.
The reason I ask this is that I once understood electricity to be a flow of electrons, but the electrons in a wire don't go at the speed of light carrying an electric current. So it's the wave that's moving at the speed of light.
Yes, or
So
close to it. Yes, it's not the electrons that that are moving fast. It's the change of the electrons, how they're pushed together, how they're drawn apart, and that is happening in waves, which of course is analogous to just barely analogous to waves in water, where the water is not moving, but the wave is moving. Next question.
John Tomaszewski?
Yes. You didn't really bring this up, but I thought maybe you could talk a little bit more about it. That these magnetic waves that are actually, they believe, is one of the reasons for that life was created on Earth. Can you talk a little bit more about that?
Yeah, I couldn't fit everything into an hour, but clearly the magnetic field of the Earth is protecting life, because if we didn't have it, we would be subject to very strong radiation. So that much is easy to understand. But then, if the magnetic field were so strong that it protected us completely, that might not be a good thing, because biology requires mutations. In order for evolution to work, there have to be changes. And those changes are partly stimulated by radiation. So it's not completely a black and white issue. But certainly, if you were looking at planets of distant star systems, and you saw evidence that a moderate-sized planet had a magnetic field, that would be an indicator favorable to the possibility of life evolving on that planet. And of course, that would imply that there was somehow a dynamo. And so then that would be a new avenue for research to see whether you could detect the presence of a dynamo creating the magnetic field. And by the way, in the solar system, most of our planets do have a magnetic field, but not all for the same reasons. For example, the big cold planets are not, they're not hot on the inside the same way that the Earth is. But they do have conducting fluids that are in motion, and that presumably produces their magnetic field.
Bill Tittle?
Right. I mean, that was a wonderful talk, and I sort of followed up. I'd be damned if I could ask a question, but here is a question. If you had given this talk 50 years ago, how much of it could you have made?
Oh, yeah, that's a very good question. Well, I said that it was in the 1950s that we first got the establishment of plate tectonics.
Yeah.
So I don't want to say 50 years ago. Let's just say a little longer. If we went back to our childhoods, that was not accepted science. And I specifically remember. I mean, it's a little silly to say this, but when I was in high school, I used to, I wanted to be a scientist, and I read Scientific American magazine. And I still remember when they had a big feature on plate tectonics, and they told this whole story of how the evidence had accumulated and how plate tectonics could explain so much about the uniformity and the differences in biology around the continents. And by the way, another thing, it turns out that Pangaea was only the most recent continental origin. Okay? Before Pangaea, the continents were again different. And you can go back, there were several cycles of continents moving around or joining together and splitting apart. So Pangaea, 200 million years ago, is only the latest one.
Okay, Meister?
Yes. Yeah, I'd like to thank Mark. It was a very well put together view graphs and nice depth and breadth on a lot of topics. I have a few comments. One is, you had the interactive video showing the isogonic lines. So it's basically going through North America, but there's also, it fluctuates over the thousands of years, but at least during the Roman times, there was one going down the boot of Africa. The boot of Italy. And
That you're talking about the animated map.
Yeah. Yeah.
Yeah, well, that was only since 1590.
okay, but if you go back in time, there was a zero igonic line going through down the ridge of Italy, and because of that,
okay. Yeah.
they can use because of that they could use a lodestone to get their latitude and longitude, and it was not a big deal, traveling around the Mediterranean. It's only when they went into the Atlantic Ocean that they needed to get a more accurate sense of what the declination is at various points of longitude.
Yeah, that's very true. When you're considering the Western world in ancient times, first of all, they didn't have compasses, but secondly, they had other ways of navigating because they knew a lot about the Mediterranean Sea, and they certainly knew nothing about declination.
Okay, and the other thing is you mentioned John Harrison, and of course there was a book written called Longitude by David Sobel
Yes, a
about
wonderful
him,
book.
which I've read, and so I guess it was in 1714. Well, there was this one um, uh, bunch of ships, British ships that ran aground, because they were doing dead reckoning and they couldn't see the sun, they couldn't see anything, and they ran aground. And so the British government put out a 20,000 pound reward for somebody to come up with a system to be able to determine longitude. So a lot of people try to do it by using the way the moon moves, but that wasn't very good way of doing it. And George Harrison, who's actually a carpenter and very good with wood, he built a wooden ship's clock that could keep very accurate time so they could determine longitude. And the irony is they never paid him, and his widow tried for years to get them to pay. But I mean, that whole story is very interesting. The other comment I have is you showed magnetite, and I guess I guess it was an iron atom, and you showed the diagram shows orbital electrons as if it were a Bohr model, but they've long discarded the Bohr model, and it was mentioned that the electrons are in Cooper pairs. Well, what I learned at college was, it's really a bunch of S&P orbitals, which is just a cloud of electrons, and not necessarily in pairs. So I don't know if they've augmented to that or not, but certainly if the electrons were outside the atom, they do travel around in Cooper pairs, as they call them. So and and of course, your other comment on Mars was, people have thought that the Mars did have a liquid core at one time and a magnetic field, and as it solidified, it would have lost its atmosphere, and if there was any chance of life there, it would have probably killed it off. So, and the moon, I think, has a similar. They found something similar, that it may have had a magnetic core in the beginning, but now it's a completely solid core. So anyway, it was a very nice talk. Thank you.
Thank you. And with reference to Mars, I mean, I have not read that anybody has figured out any way to find a record of the early magnetism of Mars. I guess if we had a colony on Mars, they might be able to find something that gave the evidence of it. So far, I think that has not happened, but it's a reasonable assumption that Mars at one time had at least a weak dynamo effect, and that, that has disappeared. And the result of that, of course, is that the surface of Mars is exposed to the solar wind much, much, much more than the surface of the Earth.
Well,
Okay.
are there any other questions?
Yeah, Phil Abruzzese.
Oh, okay.
Yes, good day. Well, thanks for your taking us on a magnetic journey to the center of the Earth, to the sun. And I guess one question is, I didn't hear the mention of, and perhaps it's an obsolete term now, of the Van Allen belts that help form the shield against ultraviolet rays from the sun.
Well, the Van Allen belts are part of the magnetosphere, and I didn't really pay attention to them specially. When the space age began, during the 1960s, we heard a lot about the Van Allen belts, and they seemed like a great, big, glorious, wonderful thing. And nowadays, nobody seems to mention them very much.
Yeah.
Because our knowledge of the magnetosphere is much more complete, and the Van Allen belts are just one little part of that. That's really all I can say about it.
I was researching the Van Allen belts some time ago, and the reason for it is I was wondering how they did the moonshot. Was the moon inside or outside the Van Allen belt? So it turns out there's two Van Allen belts, an inner one and an outer one, and the moon is outside, which means they would have been subjected to a very large amount of radiation. And there's
Yes.
some people that claim you would have needed so much lead shielding to protect them, you could have never have done the moon shot. But the other thing I read is that I think the solar spots were at a minimum or something like that. So there was actually very minimal radiation. But it's something they have to think about because they're also talking about going to Mars, and there is no protection against, the cosmic and solar radiation.
Right. And if there were a colony on the moon or Mars, people would have to live I would say, underground. They have to live under some pretty heavy shielding if they don't want to accumulate a pretty large dose of radiation.
Richie Egger?
Yeah, Mark, it was absolutely wonderful. I'm still trying to process all the information you gave me. Uh, I don't even have a good question, but I wanted to say that when I get done worrying about what AI is going to do to us in the near term, you've given me something in the longer term to worry about once we get past this AI thing. And so, yeah, just thank you so much for a wonderful presentation.
Thank you. Well, I did give you something to worry about that's potentially much worse than AI. But nobody knows. It's like what Nolan Ash used to speak about asteroids hitting the Earth, and this is the same kind of thing. Well, not the same, but certainly very large scale. If a major CME were to hit the Earth at any time, we have some protection, but not enough. And if they saw it coming, I'm sorry, I just got interrupted a little bit. If they saw it coming, they would, like a lot of satellites, for example, could be turned off in such a way that they would be resistant to the influx of particles. But equipment on the Earth, like power plants, transmission lines, radio stations, whatnot, would be quite vulnerable. They have not been designed to resist a CME, or at least not a big one. So it's a very real danger, but nobody knows the probabilities. Yeah.
Mitch Erickson?
Yeah, I just want to say that if I'm going to have to live underground, I might as well do it here and not go to the moon or to Mars. I mean, what's the point of going there if you're going to have to live underground? Just,
Yeah.
And I just read a book called A City on Mars from a couple of years ago that talks about all of the reasons that a trip to Mars or a colony on Mars is far more challenging than the proponents.
Yeah.
Like,
do you
for
remember
instance,
when we had a presenter at the Old Guard who talked about colonizing Mars a few years ago?
Right.
Vaguely, yeah.
Yeah, and he, of course, that was a few years ago, but he basically said it's much harder than people admit.
Right.
So that's interesting. I mean, yeah, you'd be living underground with a view of the, if you had a window, you'd have a view of the electrical conduits or something like that. Yeah, underground would be the way to go.
I mean, among the other things that they talk about in this A City on Mars book is having babies. I mean, the biology of having a baby.
Oh yeah.
And one thing that they don't mention in that book is crime. I mean, first of all, you got the crime back here on Earth of all of the people who would be grafting the system as we build the colony. And then once you're up there, you're gonna have the same criminals you got down here. You know, if you got a city of several 100,000 people, you're gonna have thieves and rapists and burglars and grifters and grafters, and so anyway.
Well, if only
if I'm
if
going to
only
live
we could,
underground, I'd do it here.
yeah, if only we could send all of them to Mars.
Let them fight it out.
That would
But
be
they did
better
it in
than-
Australia, you know, and you know that turned out all right.
Yes, and now the U.S. is doing that same thing, only maybe worse in some ways.
Right.
So, yeah, that's an issue.
Anyway,
but of
thank
course,
you,
it doesn't have much to do with magnetism.
John Tomaszewski.
Yeah, I asked my friend Gemini, I said, how are the Van Allen belts important? And it gave me an answer, so I thought I'd just give you a little clue. The Van Allen belts have everything to do with the magnetic field surrounding the Earth. In fact, the Earth could not exist without them. The Earth is surrounded by a magnetic region of space called the magnetic sphere, which you talked about. And it says the Van Allen belts are essentially two donut-shaped zones trapped within the magnetic fields. Here how they form. They captured particles of the solar wind, a stream of charged particles from the sun that flows towards the Earth. It encounters the magnetic sphere. The trap, the Earth's magnetic field lines up as a huge trap when the charged particles, primary electrons and protons, enter this magnetic field and they become trapped. The motion, instead of flying straight through, these particles are forced to spiral a corkscrew along an invisible magnetic field line, bouncing back and forth between the Earth's north and south poles. The result is the trapped population of high energy particles form and concentrate a ring-like structure we call the Van Allen belts. So I guess they are important.
Yeah, and so the Van Allen belts are places of high radiation because the particles are going back and forth in there. But once you get through that, then you are exposed directly to the solar wind, which is another hazard, as well as cosmic rays, which go right through, some of them go right through everything. So yes, there's all of that. And on the Earth, it's the atmosphere that protects us mostly from the cosmic rays, the ones that are not necessarily charged particles. The atmosphere protects us to a considerable degree. If we lost the magnetic field, we would lose part of our atmosphere and we'd have less protection from both the solar wind and the cosmic rays.
Yes, and I think I sent you that article that said that they have, one of the telescopes has found this magnetic sphere around one of the planets. And so they said that that's going to raise our hope for life on other planets.
Yeah, that's like what I was saying before. If you find a planet that is a plausible place for life and it doesn't have a magnetic field, that makes life less likely, at least according to our current theories of how life can exist. I mean, life without evolution is pretty far-fetched. You pretty much have to postulate an evolutionary process. And once you do that, then you realize that an excessive radiation would make that very difficult. Unless it was underground. Yeah, I should say that.
Or underwater.
Life underground is not affected by the solar wind.
Or underwater.
Yeah, underwater too. So if life began on Earth deep underwater, as some people think, then when that happened, the solar wind wasn't really involved. It's only when we come up to the surface that the solar wind is very important. So that's another interesting thing.
Gentlemen, before we depart, I know you'll all join me in thanking Mark for a wonderful.
Bill, I have a question
Yes,
and
please.
a comment. Thank you. All right. The atmosphere stripping by solar wind is a very slow process. About 60 tons of the protons hits our atmosphere every day from the sun, and our atmosphere is in trillions of tons. So it is a very slow process. Now, there are two planets in the solar system that do not have magnetic field. One is Venus, the other one is Mars. You would expect that over billions of years, them to have their atmospheres stripped by the solar wind, but they do have atmospheres. As a matter of fact, one of them is Mars has CO2 atmosphere. The Venus has a thick atmosphere. So if you are looking at it strictly from the point of view of stripping the atmosphere, you would expect both of these not to have an atmosphere. Would that indicate that both Mars and Venus had at the one time magnetic field, which basically saved its atmosphere, and since it takes such a long time to strip it, that magnetic field would have to basically disappear in both of these planets relatively recently. Now, by relatively recently, I mean millions of years ago.
Yeah, I certainly have no answer to that, but that's your research assignment, is to find out why Venus has a thick atmosphere and Mars has a thin atmosphere at this time. I really don't. That's beyond my
Right. Okay.
knowledge.
I said it's
really
just as a
don't know.
comment. Yeah.
And the only thing I could add to that is Mars, the atmospheric pressure is like 1 or 2% of what it's on Earth. So it's basically been stripped out. And as far as Venus, it's a hot cauldron that could be constant, has a very corrosive atmosphere. So there could be something on the planet that's constantly producing it.
Yeah, maybe so. And of
But,
course, there
but
are
over billions of years, you would expect that atmosphere to. I mean, particularly in Mars, you would not you expect an atmosphere. There'll be no atmosphere on Mars. Anyway, just a comment. Okay, Bill. I think we
Okay.
are ready. We should thank Mark
No,
for
absolutely.
tremendous presentation,
Yes.
and
Thank you.
I think the Olga salute is in order. So,
And it is.
All right. Thank you very much.
okay, thank you, Mark.
This has been an enthusiasm of mine for many years, and it's a pleasure to be able to express it all, and
Yeah.
to tell you why it's so interesting and why I care about it.
And I think we all learned a lot, Mark. So that's the wonderful thing about it.
And your enthusiasm came through.
Right.
Okay, everybody.
All right.
Thank you.
Thanks a lot.
Bye-bye.
Thank you, Mark. Well done.
Okay.